I'm not sure how far we went, but I think we were discussing the domain of the inverse function added to inverse function, the inverse of that. So let me just begin with fi. The domain is 0 delta I with range fi 0, fi delta I, and then fi inverse has fi 0, fi delta I, mapping into 0 delta I. And then when we looked at fi inverse plus fj inverse, the domain of this is the intersection of the domains of the ith and jth inverses, which means that I think we used aij and bij, right? Did I do that? Yeah. So it's aij, bij, mapping into now, because of the camera, I'm going to write it this way here. Where aij is the maximum of the lower bounds, so we're looking at the intersection of the domain of fi inverse with the domain of fj inverse, which means I'm looking at the larger of the lower bounds and the smaller of the upper bounds. That's how you determine the domain. And bij is the minimum of fi delta I, fj delta j. Lots of complicated looking functions and domains, but the main idea is quite, well, it can be streamlined. Okay. All right, so what did I call? We gave a name, Lij and Fj, Uij. Okay, so I guess we defined Lij to be this one. And Uij to be the same thing evaluated at the upper end of the domain. Okay. Now, either I began with Lij or Uij. Which one was the one that I did first? Or did I do both? Because I don't remember. Lij, okay. So Lij happened to be one of three quantities. The first one is 0 plus Fj inverse of Fi of 0. This is true if Aij is defined by Fi0, which is greater than Fj0. Please check your notes to make sure that this is what we had before. Okay? The second case, 0 plus 0 if they are equal. And the last case is Fi inverse of Fj of 0 plus 0 if Aij is defined by Fj of 0, which is strictly greater than Fi of 0. This is the situation. Now what we want is, we want to be able to evaluate the inverse of this sum function. So the inverse of this sum function has this as its domain, and that domain is Lij, is defined by Lij and Uij. So when you evaluate this function at the distance between I and j, you want that Dij to be between Lij and Uij. That's what you want to be able to compute or evaluate that. However, it is possible to have that distance being strictly less or outside of the domain. Okay? That's, I think, where we had to stop last time. There's no guarantee that Dij will be greater or equal Lij. That's the last point I made, which means it can be less. So in that case, if Dij is less than Lij, it actually does not pose a problem as far as solving the problem we're working on, which you don't see on the board right now, but it's in your head, I'm sure. So in that case, when Dij is less than Lij, what we have is Fi inverse Fj inverse evaluated at Aij, that's the definition of Lij, which is less than or equal to Fi inverse plus Fj inverse of Z, which is what we're trying to minimize in the actual problem. This will be true for every Z in the interval alpha prime to eta prime. Why is that true? And what's the significance of that being true? Well, first of all, what is the significance of that being true? What we had was, remember, we're trying to minimize Z subject to Fi of the distance. Well, maybe I should just refresh your memory here. This is what we've been looking at. That's what you're trying to solve, is if you recall. And we actually restricted Z to alpha prime, eta prime by pre-processing some of the data, okay, by cleaning up the data. And then we actually replaced the set of all indices by a smaller set, which actually eliminates some of the redundant constraints. So this is already done. So when you try to minimize this, when you wanted to use the Helly theorem, you wanted to actually write the constraints in the following form. Okay, so you wanted to express the constraints in this form by making sure that Z is indeed in the domain of definition of each inverse function. And that's ensured actually. And then from here, we wanted to use the Helly theorem, which said that such an x will exist if Dij is less or equal Fi inverse plus Fj inverse of z, which is the same thing as that. And this should be true for every pair I and j in I star. And because of the symmetry, you may restrict I less than or equal to j. Okay? So that simply says that, well, what does it say? You're trying to show that Dij is going to be less than or equal to that number on the right if z is restricted to the range that we actually imposed in the problem. So that's the significance. In other words, that would be a redundant condition to check for whenever Dij is less than Lij, because that will be for sure satisfied, so you may actually get rid of that. But why is this true? So I explained to you what the significance of that will be. Now the next question is, why is that true? Well, you may not be able to see it, but it's true because of the following fact. Well, alpha prime is certainly defined by the maximum of the Fi zeros, but Aij is the maximum of only two of the Fi zeros, Fi zero and Fj zero. So alpha prime is certainly greater or equal Aij. Likewise, eta prime, you can show that it's less or equal Bij. So this is a subset of that. And that means, of course, z belongs to this, which is in the domain. And so whenever z belongs to the actual small set, it belongs to the domain of definition of that. And it becomes a redundant constraint. Okay? All right. Well, I shouldn't say automatically. So this inequality is satisfied for such index pairs for which Dij is less than Lij. They become redundant. No, my set inclusion includes equality. I never write another line underneath because it's redundant. Well, with such constraints being redundant and by simply observing that Lij is always less than or equal to the maximum of Lij in Dij, the last problem we had written down can be written in this particular form, where ij is in I star I less than or equal to j, so that whenever the maximum here is realized by Lij, that indeed tells you the constraint is redundant, but this is well defined. Whenever Dij is the maximum, then it's non-redundant, but then it's well defined. Okay? So everything is well defined. Now, I don't remember what the last problem number that I used, but in my notes, this is P5. What was it before? I'm not sure if we... P2? Maybe I just skipped certain numbers. So let's call this P3, but you must remind it of me. Okay? Now, before I proceed any further, so I'm going to focus on P3 as far as the lower bounds or Lij's are concerned. What about the Uij's, though? So, how about Uij's? The question is Dij always less or equal Uij? That's a more critical question. Now, again, if you look at the definition of Uij, it's Fi inverse plus Fj inverse at Bij. So this is going to be equal to one of three quantities. The first one is delta I plus Fj inverse of Fi of delta I. This is true if Bij is defined by Fi delta I, which is strictly less than Fj delta j. The second one, delta I plus delta j. If you have equality here and equality here, if everything is equal. And the last case, it will be Fi inverse of Fj of delta j plus delta I if, again, you have, well, let me just write it. Bij is defined by Fi. No, there's something wrong here. Just a second. Fj, yeah, okay. Yeah, if the rows of I and j are swapped. Now, here we know that Fi is a non-negative valued function, which means its inverse is also non-negative valued, which means that when you simply drop the complicating parts, you will have, what will you have? You will have the following. The distance Ij will be less than or equal to the distance or the minimum of delta I and delta j. Anybody agreeing with that? Well, you should, because delta I is the farthest distance from I, delta j is the farthest distance from j, so a particular distance between I and j will certainly be less or equal that, okay? And I'm sure you all agree that this is less than or equal to uij, because each term is, because of these complicating terms being non-negative, uij is less than or equal to the dropped versions of these, okay? So, I just showed that the ij actually does not exceed the upper bound, so that's a pretty good result. Accordingly, the last problem I wrote down is well-defined. Let me rewrite it again. P3, yes. So we're looking for as small as z here, which is the output of the minimization problem, subject to fi inverse plus fj inverse evaluated at maximum. Did I put down the inverse here before? Did I? Yeah, because if I forgot, put it in. Yeah. Maximum of distance ij and lij less or equal z. This should be for each I and j in I star with I less or equal j plus z in the interval alpha prime to eta prime. What do I mean by P3 being well-defined? What I mean is this argument here is always in the domain of definition of this complicated looking function. And z is always greater or equal to that. So, all right. First of all, the case I equals j is already handled by the restriction of z to values greater or equal alpha prime. Okay? Because alpha prime is the maximum, well, you can actually figure that by doing it on the sides. Okay? The minimum feasible z, i.e. the value of z star, is given by the maximum of either alpha prime, which is this bound on z, or something else, which will come from the above, beta prime, where beta prime is the maximum of the beta ij values maximum over pairs ij for which I is strictly less than j, because I equals j is already handled by alpha prime. And what's beta ij? Beta ij is the largest of these bounds here. Well, sorry. Beta prime is the largest of those. Beta ij is simply that number. By definition. So let me reiterate. P3 is equivalent to the original problem we had. We cleaned it up so that it becomes solvable. When you cleaned it up, it turned into a problem of minimizing a single variable z subject to a bunch of lower bounds. Z is bounded below by each left side here. Each left side is a beta ij number, the value, and these are all computable in terms of the original problem data. So z is greater or equal each of these terms. Z is also greater or equal alpha prime, which means, of course, the minimum feasible z will be either alpha prime or beta prime, where beta prime is the largest of these left sides in the complicating constraints. Okay? So from our earlier discussion, of course, we know that z star is bounded below by alpha, which is the version of alpha prime defined relative to all vertices rather than the restricted set of vertices. Anybody remember this? Alpha was defined relative to the set of indices I, where that contains the indices 1 up to n, okay, all vertices. But then I cleaned it up and I compute this relative to I star. Okay, that's what we did. I star are the critical indices that eliminates redundancies. Okay, so this is certainly true. So we may replace actually z being greater or equal alpha prime by this, okay? Why am I doing this? Because I do not wish to really deal with the set I star. I pretend that I know it, but I'm trying to revert back to the original problem data without having to do any pre-processing. Okay? So I got rid of alpha prime. Now I want to get rid of also beta prime to make it beta. So to compute beta prime, we need to know the set I star. However, this is really not necessary. If we define beta to be the maximum of beta ij's, I and j belonging to I rather than I star. No, this is I. I replaced it with the original set of vertex indices. Okay. So at home you might want to work on y beta equals beta prime. So we conclude that Z star is actually the maximum of either alpha or beta. There are a bunch of other stuff here, but let me get to the actual point here, because I don't want to spend too much time on this. So the basic idea is this. First, you compute the optimum objective value. Once you compute this, you know one thing. What do you know? You know that if Z is taken to be Z star, then the constraints have a feasible solution X, at least one feasible solution X. And because of the monotonicity and because of the neighborhood intersection property, that will be a unique solution again. The only thing that remains is, how do I find that unique solution? One way is to compute the composite neighborhood intersection. Okay? But so let's put that as a note here. So we may compute the unique feasible point X star, which is the optimal point actually, corresponding to the optimizing value of Z star, by finding the feasible solution to the distance constraints X Vi less or equal Fi inverse of Z star. I'm running out of board markers here. They don't seem to be doing the job. Yes. Now, I know that Z star actually is that value which permits a feasible solution. So this is guaranteed to have a feasible solution. Furthermore, it's the smallest such Z star. So this has at least one feasible solution, but it will turn out that it will be a unique solution. the feasible set for this is defined by the composite neighborhood representation, which takes the unique solution x star as your radius. So this is the intersection of all these neighborhoods around each vertex vi, with fi inverse z star being the radius, I going from 1 to n. If anybody remembers what we did in the linear case, we will do the same thing in this case. What did I do in the linear case? This composite neighborhood is actually defined by two critical vertices, or maybe one, okay? Either one or two. If z star happens to be alpha, which equals fs0 value for some index s, which is of course greater or equal, well, in this case it will be greater, fi of 0 for I in I, then the particular constraint relative to Vs will be equal to Fs of 0, which means that the distance between x and Vs must be, sorry, just a second. No. It's not 0. It is Fs of inverse evaluated at z star, which is equal to Fs of 0. Yeah. Now, how much is this? This is 0. Which means that the only feasible solution you have is x star equals Vs. So this simply tells you that whenever z star is defined by alpha, which will be supplied by some index, then your optimum point is on top of that particular vertex. You cannot deviate from that. It's too large. The 0 value is too large. Esra, okay? You seem to be questioning there, huh? In the remaining case, z star is strictly greater than alpha, which means it's supplied by some maximum beta ij value, which is, say, beta st, where s is different from t. And the constraints corresponding to these, well, you've got two constraints. One is this one, the other one, this one, with Fs inverse z star, the other one Ft inverse z star, which happens to be Fs inverse beta st admit a unique solution star y. Because if you add up these, you get dxvs plus dxvt, which gives you fs inverse plus ft inverse beta st. I'm adding the left sides and the right sides, so, oops, that's less than or equal. We get this inequality. What do I know about the distance between S and T? Due to triangle inequality, you've got that. What do you think this will output? It will also output dst if you just go back to the definitions of beta, etc. Okay? So, because this is going to be also equal to dst, all inequalities hold as equalities. So x star in this case is the unique point on the path connecting S to T for which the distance between x star and Vs, when you evaluate it at the loss function associated with S, is equal to Z star, which is also equal to Ft, evaluated at the distance between x star and Vt. So you just found the point at which these two loss functions are equal. You should be able to show this part, that the output of this is dst. Okay? It's pretty straightforward. But all this says is the following. I've got Vs here, and I've got the path connecting them, Vt. This is not an edge, that's a path. That's the unique path connecting them. And Vs or Fs is some kind of a monotone increasing function going the same in each direction. This one is also like that. And at the point they intersect, when you look at the distance between x star and Vs, the first function achieves the same value as the other function, Ft function, at the other distance. Which means that the height here, Z star, is defined by both of them. And locally, the f function is defined, well, f is the maximum of all these vertex-related loss functions. Locally, at around x star, it's defined by only these two indices, okay? The other ones are dominated, whatever. They may be going like this, whatever, okay? We're out of time, so we stop here.